Yeah, thank you. I'm very happy to be virtually back at CWI. And this work was also inspired by one of the CWI people, Bravyi. Unfortunately, when he was there, I didn't know about his work on stabilizer rank, but when I started my second postdoc, I was interested in this question, stabilizer rank, and I really enjoyed reading his work. The outline of today's talk, I try to give the motivation, why do we care about this stabilizer rank, and some definitions, background. Then I talk about what we know about this stabilizer rank and what we could prove. And then I try to outline the proof. And then finally, I talk about small complexity theoretic implication of our result. It's related to something called quadratic uncertainty principle. Okay, to begin with, we are all interested in quantum algorithm. In general, we can think about a quantum algorithm as we have some classical input X, we encode it into some quantum state, usually in computational basis, and then we apply some elementary gates, and at the end we measure some qubits, and that's supposed to be the output of our algorithm. And we can usually assume that this U1 to UM, these unitaries are coming from some universal gate set. And there are different universal gate set. One example of that is this one is C naught H S and T. These are not important. What is the definition of these things? But these are just for unitaries. And the important question underlying this quantum complexity theory is that if we are given the classical description of this circuit, can be simulated classically or not? And we believe that it's not possible to simulate it efficiently. But to get a better understanding, if you look at this gate set C naught, H, S, and T, people realize that this T is a bit different from the others. And to formalize it a bit more, there is a whole framework of a stabilizer formalism that I try to just recall. You'll probably know better than me. I try to give the definitions of this stabilizer formalism. The first ingredient is this Clifford group. It's a subgroup of the unitaries acting on n qubits. There are two equivalent definitions. The first definition is just, it's very related to that universal gate set. It's all the unitaries that you can construct using these three elementary gates, C naught, H, and S. So I just exclude T and I look at the group generated by these three gates. And the other equivalent definition is the normalizer of Pauli group. You probably know the definition of the Pauli group is the tensor product of this I, X, Y, and Z. And the Clifford group is the set of unitaries that if you conjugate the elements of the Pauli group, they remain in the Pauli group. So I just want to emphasize that we have these two equivalence definitions. The first one is based on the circuit model, and the second one is more algebraic definition. And they're equivalent, and sometimes it's easier to work with one definition in different contexts. The second ingredient is the stabilizer states. Again, we have two equivalent definitions. The first definition is again has circuit flavor. This Clifford group, it has some action on this Hilbert space of n qubit states, and the stabilizer states are just the orbits of this group action containing the zero state. So if I start with this 0 to n, and I apply some Clifford, then I get a stabilizer state. And this is the only way to get a stabilizer state. And the second definition, which is equivalent, but again, it has more algebraic nature. It's saying that the stabilizer states are the states that are stabilized by some subgroup of the Pauli group. So if a state is a stabilizer, if you can choose n elements of the Pauli group that are independent, that is, you cannot write one as the product of others, and they're also commuting, and all these Pauli elements, they stabilize your state. If you apply that Pauli element on your state, it remains the same. There are very important examples of this stabilizer states. For example, all computational basis states that are stabilizer states. Also, the Fourier basis is a stabilizer state. And there is a famous example, for example, the EPR pair, it's also a stabilizer. If you look at this state, you can easily check that it's stabilized by XX and ZZ. So if you apply these two operators, it remains the same. Okay. Now we have this very important theorem predicted due to Gottesman and Neal. It basically says that if you start from a stabilizer state and if you apply some Clifford operation, you still get a stabilizer state. It's easy to check from the definitions. And it says that there exists some efficient classical algorithm to find the output of this circuit. So if I give you the classical description of the input and the circuit, you can, in polynomial time, compute this classical description of the output. And the proof is also not that complicated. You should use this definition, the second definition of the stabilizer state. If you look at the input, you can describe it by n Pauli operator that stabilize this state. And when you apply some Clifford operation, you can keep track how these n operators are changing. And there is a table, you can find it in Nielsen and Chong book. Each Clifford operation change a few of these operators, and at the end you can find the Pauli operations that stabilize your output. And one small remark here is that in your circuit you can also have some measurement in computational basis, and you can still have efficient classical simulation of this quantum circuit. Okay, so far we have seen that you can the quantum computers work with 4 gates, and if you have only 3, you can simulate it with classical algorithm. So in some sense, the power of quantum computers are coming from these T gates that are not in that Clifford group. And you can check that you cannot even approximate these T gates with the Clifford group. So these Clifford groups are not universal. And even though we cannot, although you cannot approximate these T gates with Clifford group, there is something called gadget base or teleportation of this T gate that looks like Clifford group, and it's as follows. You can see that these two, this one and this one are exactly equivalent. Here you have some ancilla qubit. It's initialized in this state called T state, and it's this one, I forgot the normalization. And then you apply a C0 and you measure the second qubit, and based on the measurement, you apply S gate on your first qubit. And you can check that it's exactly equivalent to the T gate. And the important point here is that everything here is either a Clifford operation or a measurement. Just you need to initialize the ancilla qubit in this state. So if you use this gadget-based implementation of this T gate, you can if you have some arbitrary quantum algorithm, you can write it as some Clifford plus T gates, and then using this gadget-based, you can convert your algorithm to something like this. It only has Clifford and measurement, but you have some ancilla qubits initialized in this state, C tensor power k, and k here is the number of T gates you have. So if k is 0, you don't have any ancilla qubits and you can simulate it classically, but if k is non-zero, then you have some ancilla qubits and believe that it shouldn't be that there shouldn't be some classical algorithm to simulate that. So far, I've seen that if you have some quantum algorithm, you can always find this kind of implementation. The operation are just Clifford and measurement, but you have some ancilla qubits initialized in this T to the power k. Now I define this notion of a stabilizer rank. In general, if I have some n-qubit quantum states, phi, I define the stabilizer rank in this way. It's the minimum number R such that there are some R stabilizer states, S1 to SR. And there are also R coefficients. Sorry, this should be C. And you can write your state as a linear combination of this S1 to SR. And you have some approximation parameter delta, and this can be arbitrary. And there is some terminology that if delta is 0, we call it exact rank. And if delta is greater than 0, we call it approximate rank. And if delta is 0, we usually drop this subscript delta. We just write chi of phi for exact rank. Just to give some example, if you have some stabilizer state, then the stabilizer rank is just 1 because you can write it as itself. You don't need anything. And if, for example, you look at this T state, it was like this. Then it's not a stabilizer state, so you cannot write it as one stabilizer state, at least for delta small enough. But you can write it as 2 stabilizer states. In fact, this 0 and 1, they are both stabilizer states. So for delta small, then delta of T is 2. And there are some, for example, simple relation. For example, the stabilizer rank of 2 product state is always less than the stabilizer rank of the product of the stabilizer ranks, because if you tensor product to a stabilizer state, it's still a stabilizer state, but it's not necessarily tight. Actually, it's difficult to find a state that this inequality is equality. And one final remark for this definition is that the stabilizer rank is always upper bounded by 2 to the n, because you can always write any state in computational basis, and computational basis the elements of computational basis are stabilizer states. So we have this simple upper bound on the stabilizer range. Now, how is related to what I discussed before? We have this theorem that there exists some classical algorithm that you can give it the description of some arbitrary quantum circuit. It's the circuit size is n, and it has k t gates. Then it can simulate this. The classical algorithm can simulate your quantum algorithm, and the complexity is related to it's polynomial in n, but it's related to the stabilizer rank of this t to the power k. And to see that why this is true, it's not difficult because, for example, if this one is some number r, then you can write your state, or approximately your state, as sum of some stabilizer states. And here, your circuit. If we look at this slide, we can write write our circuit in this way. And here we have this t to the k and your input. And here you have Clifford plus measurement. And since we have this decomposition here, you can decompose it. You can write it in this way. And now I can simulate this circuit for each input Si. So what I do for every I simulate this circuit. Here I have X, and here I have Si, and here I have a circuit of Clifford plus measurement. And I can do the simulation classically using the Scattesman-Neal theorem, because here the input is stabilizer and the circuit is just Clifford and measurement. And then, due to the linearity of the quantum circuit, I can find the outputs here. Sorry. So here, if this state is phi I, here is just sum of alpha I, phi I. Right? So I can simulate any quantum circuit. Just the cost of the simulation depends on this number R here. The number of stabilizer terms that I need in the decomposition of t to the k. So I hope that.
Sorry, Mehrdad. I seem to recall from the literature that there should be a square here, right? Because if you want to actually sample, if you want to actually produce like a measurement outcome, because like here right now you get the sum of Cliffords, but in order to actually do something with this, you either need to represent all the Cliffords as a state, in which case you need exponential space, so you don't want to do that. Or you could do something like calculate marginal probabilities and then use those to get a sample out. But in that case, you would need to create a marginal diagram which squares the number of terms. Because also, if you stabilize the extent, you also get a square in there for this reason.
That's a very good question. Yes, if we do it in the way that I described, you need a square here. And I believe that the first papers that they use this idea to simulate quantum circuits, the complexity was this stabilizer squared. But there are some smart way of avoiding that square. That you need to use some other ideas. But yeah, that's a good point. Yeah, you need if you do it the way I describe it, you need the square, right?
Okay, thanks.
Okay, is there any other question? Okay. Okay, so I hope that you are convinced that this stabilizer rank is a relevant quantity, and it's related to the cost of one specific way to simulate quantum circuits classically. And now it's important to study what is the value of this stabilizer rank. And there are some upper bounds and lower bounds on this stabilizer ranks. The best upper bound we have some upper bounds for the exact rank, and we have some upper bounds for the approximate rank. They're both exponential with different exponents, and we believe that these are at least the stabilizer rank should be exponential. We don't know whether the exponent is tight or not, but we believe that the stabilizer rank should be exponential, or at least super polynomial, because otherwise BQP would be equal to BPP, and we believe that that's not true. And before our work, the best lower bound for the stabilizer rank were as follows. We had a linear lower bound for the exact rank, and we had a square root lower bound for the approximate rank. These results were established by 3 independent groups, and one was the work of Farrokh-Labib. Actually, the technique used by Farrokh-Labib, he couldn't use it for the approximate rank, but he had a more general result for the exact rank, and he could prove the linear lower bound for the exact rank. And you can see that there is huge gap between the lower bound and upper bounds, and we believe that we should be able to improve the lower bound. And this is the result that we could prove. We could prove that for any approximation parameter delta, the approximate rank of this t to the n is lower bounded by a quadratic term, n squared. You have a polylogarithmic term, and you have also this. We have this coefficient depending on delta, and if you just compare it to the previous result, we improve both these lower bounds to quadratic, and also in the previous results, the lower bound for the approximate rank, they did delta to be small enough in all previous results, but in our result, this works for any approximation parameter delta.
But delta can be 0 or not? Your result.
It can be 0. Yeah.
Actually, because it says it cannot be 0.
Okay. Sorry. It should be. Yeah. Actually, if you prove for a non-zero delta, it immediately implies a result for delta equal to 0, because the exact rank is always larger than the approximate rank. Okay. Yeah, that's just one more remark that I want to make here, is that even for delta n going to 1 with some appropriate speed, it shouldn't go to 1 very fast. This result is still correct, but it wasn't very interesting. We didn't state our result in that way, but even we can have some delta that is very close to 1. It means that even if you want to approximate your state with very terrible approximation parameter, you still need quadratic terms, a quadratic number of stabilizer states. Okay. Now I want to give the main ingredients of our proof. Just before talking about the proof, it's good to compare our proof to the proof of the previous results, all the results proving linear lower bound. They use different techniques. They have very smart ideas in the proof, but the flavor of all the proofs were very similar, and it was as follows. They considered one specific feature of this state t to the n. For example, you can consider the maximum overlap of this state with all stabilizer states. And then they proved that if you want to capture this particular feature, you need a linear number of stabilizer states. So if you have, for example, a square root n number of stabilizer states, you cannot have that specific feature. And the feature that they considered and the tools that they used were very diverse. They used very interesting tools. One work was using tools from linear algebra. One was that the Farrokh-Labib work was using the tools from high order Fourier analysis. And the other work used tools from number theory. And yeah, they were very interesting work, and but they all stopped at this linear lower bound. The way that we thought about this problem was a bit different from those work. We said that proving a lower bound for this T state is also called magic state. It's difficult. Other people tried, and the best thing that they could prove is a linear lower bound. We tried to consider the stabilizer rank of a random state. So you sample some n-qubit random state according to the Haar measure, and just out of curiosity, you can ask what is the stabilizer rank of that state. And the interesting result that we could prove is that the stabilizer rank of a typical state, or typical Haar measure sample state, is almost 2 to the n. And if you remember, we had the lower bound, we had this upper bound 2 to the n. So it means that almost all states, the stabilizer rank is very close to the maximum value. The next thing is that you can use the ideas that I talk about. Okay, no, sorry. The next step is that you can always prepare a random state with Clifford gates plus, sorry, it should be 2 to the n over 2t gates. So this random state that we know that the stabilizer rank is large, we just prepare it with Clifford and 2 to the n over 2t gates. And then we use that idea of teleportation that I talked about in the beginning to replace each t gate with some ancilla qubits and this t to the power 2 to the n over 2. And now you can see that if I can relate the stabilizer rank of this state to this state phi, then I have this equation, stabilizer rank of. Suppose I can relate it. I will talk more in details about the proof, but suppose that I can relate it to the stabilizer rank of this phi. Then I know that this is almost 2 to the n. And then I can change a change variable and call this 2 to the n m. Maybe I should call it ms squared. And then this is m, and I prove what I want to prove. This is the general idea. Now I'm talking more details about each of these 3 steps that I talked here. The first step was the stabilizer rank of some random state. And the result that we could prove is more general than just the stabilizer rank. If I consider some arbitrary subset of n-qubit states, and the only thing that I know about this arbitrary subset is that the size of the subset is bounded by 2 to the some polynomial in n, and I have some random state sampled from the Haar measure, and this Haar measure means that you sample uniformly from the unit sphere. And I defined the rank with respect to this arbitrary subset. So if you look at this definition of R, is exactly the definition of the stabilizer rank. Just I replaced this stabilizer states with this arbitrary subset of the n-qubit states S. And we have this result that the probability that this R is greater than 2 to the n over some polynomial in n is going to 1. Just before giving the ideas of the formal proof, I want to argue that this is what we should expect. Because if you consider some random state, you need almost 2 to the n bits to represent it. This is just some intuition about a random state. And if you have a state of size 2 to the polynomial n, each element of this subset S, you need a polynomial number of bits to represent that element. And if I can represent my state in terms of the elements of this, for each one, I have a polynomial number of bits. And so the number of terms that I need should be at least 2 to the n over some polynomial. This is just some intuition why this result should be true, but so each term has some polynomial number of information, so you need 2 to the n over some polynomial number of these terms to represent your random state. Yeah, this is just intuition. To have some formal proof why this result is true, we fix some fixed elements of this subset S, for example, S1 to SR. And this S1 to SR, they define a subspace of your whole space. The subspace is spanned by these vectors. And this is at most R-dimensional subspace. So in this picture, you have your random state phi, and you have this subspace spanned by S1 to SR. And if for fixed vectors S1 to SR, you can always decompose your random state into 2 parts. One part is inside this, so maybe it's difficult in this picture, but you have some orthogonal part and some part that is inside this subspace. So, and if you denote by P the projection onto this span, then you have this part that is inside the subspace and the part that is orthogonal to your subspace. You can always write your state in this way. And if we can prove that with high probability the norm of this part is small, then you cannot represent your state phi in terms of S1 to SR. So sorry. Here, the probability that the norm of this vector for a particular value of S1 to SR is greater than 1 minus delta S squared, we can show that it's very small. It's if you look at this upper bound is double exponential, it's e to the power some exponential number. And to show this result, you have to use some concentration inequality, in particular this Levy lemma. You can prove this result, that for a particular value of this S1 to SR, this probability is small. And then if you use very naive union bound, you can show that the probability that there exists some S1 to SR, that this norm is large, then it's going to 0. So this means that you cannot choose R elements that your state phi is the component that is inside the span has large norm. And you can see that this statement is equivalent to because I define it for arbitrary subset, this is equivalent to this one. So if you look at the complement of this event, you get the result in the statement of the theorem. Okay, this is the proof of the first step. In the second step, we need to approximate some random state with Clifford and T-gates. So if I have some arbitrary n-qubit state phi, using just basic Solovay-Kitaev theorem, we can show that there exists some circuits consisting of 2 to the n order of 2 to the n Clifford and T-gates that approximate your states with very good approximation. This is actually true for any universal gate set, and since Clifford plus T is also a universal gate set, you can always choose 2 to the n gates such that the output of your circuit is very close to the random state phi. And when we first put our paper on arXiv, we thought that this result is tight. And my intuition was that because we know that this 2 to the n for the total number of Clifford and T-gates is optimal. And my intuition was that this Clifford operation are almost, I thought that they are almost free. So the number of T-gates should be also 2 to the n, or at least of the order of 2 to the n. But after we put our paper online, we find very interesting result that you can decrease the number of T-gates significantly in your circuit. And there is a result that is showing that you can have a circuit. It has a lot of ancilla qubits, but it consists of Clifford plus 2 to the n over 2 T-gates. And the output of this circuit is very close to your random state, and the ancilla qubits are clean, that they are at the end of the circuit is in the 0 state. So you are increasing the number of Clifford by very large factor, but you are decreasing the number of T gates in your circuit a lot. So far we have this random state. We know that the stabilizer rank is large, and we also can prepare this state using this circuit. Yes, is there a question? Okay. Now I'm going to talk about the third step of the proof. In the previous step we had this circuit that consists of Clifford plus 2 to the n over 2 T gates, and it could prepare the random state that has high stabilizer rank. Now we use the idea of the teleportation of T gates to replace each T gate by a Clifford circuit and some measurement. And we need to add some ancilla qubits here. And for each T gate, we need to add one ancilla qubit, and the whole these all ancilla qubits, they are initialized in this state T to the power 2 to the n over 2, and this 2 to the n over 2 is the number of T gates we had in the first circuit. Now we could prove some basic lemma that if you look at this circuit, it has a Clifford plus some measurement, and it has some input ports initialized in 0 and some input ports initialized in T to the n, and the output is some state phi. Then we can show that the stabilizer rank of sorry, here should be delta. The stabilizer rank of T to the n is lower bounded by the stabilizer rank of the state phi at the output of your circuit. Now I can put everything together. I had this state phi, and I know that this is greater than 2 to the n poly n, and I had this circuit that I had 2 to the n over 2, 0, and I had this phi, something close to phi, and 0, and here I had this Clifford plus measurement, and I can use this lemma here to conclude that the stabilizer rank of phi is less than the stabilizer rank of 2 to the n over 2. And if I use this result, this is over poly n. And here I just, again, I define m as 2 to the n over 2, and then I get the stabilizer rank of T to the m is lower bounded by m squared. Is there any question? Okay. Now I want to talk about a small implication of our result in the complexity theory. It's not very important question in the complexity theory, but it was interesting to use these techniques from quantum computing to be able to say something about completely classical complexity theory. In general, there is this notion of rank that for Boolean functions, if you consider a subset of all Boolean functions f, and if you consider one particular Boolean function, we can define the minimum number of terms you need from from this set f, such that we can write -1 to the power g as this linear combination of this -1 to the power fi. And one particular examples that people studied before is when this subset f is all quadratic polynomials, and this function g is AND function. And there is some conjecture called quadratic uncertainty principle that's saying that the minimum number r for this particular example should be order of 2 to the some alpha n, or some alpha constant. But the best lower bound that people could prove is n/2. Again, there is a huge gap here between what we believe is true and what we can prove. There is a result by Ryan Williams that he proved that for any k, you can find a function in NP, a g in NP, such that that r I defined in the previous slide is omega of n to the power k. So it's for any polynomial, you can find a function that you need that many quadratic terms to represent your function. But it was an open question that whether you can replace NP by P. So can you find some function in P that you can compute it in polynomial time, and you still need a lot of quadratic terms to represent that function? And there was no known function in P that we know that the number of terms you need is superlinear. But some immediate consequence of our result on a stabilizer rank is that there is a function in P such that you need n squared, at least n squared quadratic terms to represent that function. And the reason is you should look at this T function in computational basis. It's 2 to the n/2 sum over x e to the I over 4. The weight of x. And if you look at this function, this is something that you can find it in polynomial time. Actually, in linear time, you can find the weight of x. And we proved that you cannot write this function in terms of the stabilizer states. And stabilizer states are some special case of these quadratic terms. So you cannot write this function in terms of the quadratic functions using less than n squared terms. So this was something that some implication of the result on the stabilizer rank in the completely classical complexity theory setting. At the end, I want to discuss some open questions that we still have. One obvious open question is whether we can improve this quadratic lower bound to anything better than quadratic. We believe that the optimal bound should be exponential. And can we prove something like that? And we believe that at least to use our proof technique to get something better than quadratic, we should be able to analyze the stabilizer rank of some other distribution than the Haar measure. The Haar measure simplifies the analysis a lot, but we couldn't go better than quadratic using the Haar measure. One very simple distribution that we cannot analyze yet is this distribution when this phi and psi are both Haar measure and independent. Can we show something? Can we prove something about the stabilizer rank of this state? If we can get some tight bound, I believe that we can improve the stabilizer rank, the lower bound and the stabilizer rank. There is also some questions motivated by the work of Farahlabi relating to the connection between other measures of stabilizerness. For example, if you consider the maximum overlap with stabilizer states and the stabilizer rank, can we prove any connection between these measures? And this fidelity that I call here is that maximum overlap. And for this T state, we know exactly what is the maximum overlap. So if we can prove some connection, we might be able to improve the lower bound. And the last question that might be interesting is this robustness of a stabilizer rank. We know that there are some states that the approximate rank and the exact rank are very different. There are actually some examples that the approximate rank is 1, but the exact rank is 2 to the n. But can we say something more concretely about the robustness? For example, if you have some typical state, what would be the robustness of the stabilizer rank? How that approximation parameter affects your stabilizer rank? And this could, for example, right now we have a quadratic lower bound approximate rank, but can we get something better than quadratic on the exact rank from that lower bound? Yeah, that's this open question that I thought might be interesting. And with that, I conclude my talk, and I appreciate your attention, and I would be happy to answer any question.